In this video, we'll talk about the definition of the definite integral. So we say that a function is integrable if we can find the area under its graph by using a limit of Riemann sums. That is, we can sort of approximate the area by rectangles and then take the limit as the number of rectangles to infinity, and that will give us an area for this region of the graph of this curve. The important thing for it to be integrable is that no matter how we pick our heights for rectangles, we always get the same limit. And in this case, the limit we get, which we'll call L, is the definite integral of f over the desired interval. And notationally, we write this as L equals integral sign from A to B, A to B telling me the interval over which I'm finding this area, f of x. So from this notation here, we have the integral sign. This tells us we're doing an integral. We have our limits of integration, a and b, basically telling us our starting point and ending point for this area. In terms of the area in the graph, they are the left and right boundaries of this region we're finding the area of. We have our integrand, which is the function that's inside. And we have a differential dx here on the end, which basically tells us what variable we have for this integration. A point to note right now, this x here is what's called a dummy variable. What I mean by that is it doesn't matter what letter I use there, the value is always the same. I could write the integral from a to b, f of t dt, integral a to b, f of r dr. All these give me the same number. And I think the note for all these integrals, these definite integrals are always a number. They're an area under a curve, so they are a number. So what functions are integrable? For what types of functions can I actually find the area via this method? The answer is a lot of them. The function has to be pretty bad for it to not be integrable. So theorem 1 tells us that things like continuous functions are integrable, which means things like polynomials, exponential functions, trig functions, all these are integrable. And the key thing this means for us here is the fact that since they are integrable, it means it does not matter what Riemann sum I use to find the area, I will always get the same answer, because the fact that it's integrable means it does not matter what I pick. So I can always pick a lower sum, always pick an upper sum, always pick a midpoint sum. Any of those I can use whatever I want. I will always get the same answer in the limit, no matter what I choose. There are also examples of some non-continuous functions that are integrable. The basic rules of the function can't be too bad. So as long as I only have a jump or have a couple jumps, that's totally fine. So a function like this, that function is integrable. It only has a finite number of jumps, and everything else is nice and smooth. This function is integrable as well. So basically, pretty much any function you could write down is integrable. There are examples that aren't, but they're pretty far out there. How do we compute these definite integrals? Well, at this point, the only technique we have is to go through the limits of Riemann sums. Right, so it's taking your function, dividing the interval up into rectangles, finding the heights, and then taking a limit. One example of what you might get here is if you take left endpoints and evenly spaced rectangles. The point is, if I know my function is already integrable, I can pick any particular method I want for making a Riemann sum, and the limit of that sum will still give me the right answer. So I can pick left endpoints, evenly spaced rectangles, and the idea is if you want to find the definite integral over the range from a to b of a function like that, f of x dx, you can find it by the following formula. And this comes from how we wrote out our formulas for areas of rectangles before. This b minus a over n is the width of each rectangle. This f here gives me the height of each rectangle, because this a plus kb minus a over n gives me the left endpoint of each subsequent rectangle in this arrangement. If you wanted to do right endpoints instead, you could change the k equals 0 at the bottom to a k equals 1, and then the n minus 1 to an n on top, and that would give you the right endpoint evenly spaced rectangle sum as well. But because we know it's integrable, either of these work and they both give us the same limit at the end of the day. So whichever one you want to use to compute these, you can do it that way. So that's the idea of the definite integral and how it comes from the limits of Riemann sums, and this new notation we have for defining the area under the curve as a definite integral.